Hello everyone, welcome back. Today let us see lesson number 5, Parseval's theorem. In this lesson, after completing this lesson, students will be able to state and prove Parseval's theorem and able to represent the condition for half-wave symmetry. So what do you mean by the statement of Parseval's? So according to Parseval's, if x of t is a continuous time domain signal with t naught as time period, the Fourier coefficients an, then the average power p of x of t is given as p is equals to 1 by t naught integral t naught x of t whole square dt equals to summation n equals to minus infinity to infinity a suffix n square. Here the x of t and an are represented under the modulus values, so only positive values. So as we are considering square term, so the respective resultant will be a positive only. Hence in Parsons, the formula is given to average power, and according to this Parsons theorem, let us see the statements as per how it is going to be justified. So as you know, the average power of periodic signal is given as 1 by t naught integral of t naught x of t whole square dt. Here x of t is represented in terms of x of t into x conjugate of t, as according to the condition property what we have already discussed earlier. So x conjugate of t, x into t, sorry, x of t and x conjugate of t will be a resultant which used to have x of t whole square. And according to Fourier series, this x conjugate of t can be expressed as summation equals minus infinity a suffix minus n conjugate into e power j n omega naught t. This is according to properties what we earlier discussed for Fourier series. So, and x of t is a complex value. Then only the conditions will be satisfying as per the equation 2. If x of t is not a conjugate, then the condition directly considered as square only. That is the first expression as we can see in the statement here. This statement is valued when x of t is a periodic signal without any complex. If x of t is a complex, then this will be satisfying provided the x conjugate of t according to the property of Fourier series, the resultant of coefficient of Fourier series a suffix n will be modified to a suffix minus n with conjugate. Next, substituting the x conjugate term in this one, we get as shown in equation 3, and rearranging the order of integration wherever the t function is there, the integral can be represented across those terms as a suffix minus n conjugate is a constant, so it will be kept outside the integration and the remaining terms will be represented within the integration. Hence, according to the definition of Fourier series, as you know, the a1 coefficient is given 1 by t naught integral 0 to t naught x of t into e power minus jn 2 pi by t naught into t, where 2 pi by t naught nothing but omega naught. So replacing this equation 5 in previous equation, we get a suffix minus n conjugate into a n. Here n must be a suffix, so by mistake it is typed in normal font. Here consider this n as a suffix, so the condition will be modified with a minus n conjugate with a suffix n equals to a suffix n square. Hence, the left hand side condition what we have considered earlier, 1 by t naught integral of t naught x of t whole square dt will be equals to summation n equals to minus infinity to infinity a suffix n whole square. Next, what do you mean by this half-wave symmetry? Half-wave symmetry. Half-wave symmetry, according to symmetry condition, the waveform whatever defined in the positive side, the same waveform must be defined in the negative side. Similarly, if the two halves of one period of a periodic signal are of identical shape, except that one is the negation of the other, the periodic signal is said to have half-wave symmetry. That is, if x of t is a periodic signal with period t naught, then x of t has half-wave symmetry if x of t minus t naught by 2 is equals to minus x of t. Okay, that is what half-wave symmetry has been defined. And with this, we complete this lesson. Let us meet in the next lesson. Thank you.